Good morning, students. We will start Fourier series today. So I will define for first of all what's meant by a trigonometric series. Okay. Now a series, consider a series of the form C a naught by 2. A naught is some constant. Okay. Plus summation n equal to 1 to infinity an into cos n pi x by L plus summation n equal to 1 to infinity bn into sine n pi x by L. See, if I simply write, it as say, or we will consider this later. So first consider a series of the form a naught plus a1 into cos x plus b1 into sin x plus a2 into cos 2x plus b2 into sin 2x. Yes, plus now next term is a3 into cos 3x plus b3 into sin 3x plus etc. Yes, now I think you have got the pattern, right? So a naught is a constant. Now after that, with ai's cos terms occurs. Okay, so a1 cos x, then a2 cos 2x, then a3 cos 3x, and so on. Okay, so you will have a4 cos 4x, a5 cos 5x, and so on. Now with b1 sine terms occurs. So b1 sin x plus b2 sin 2x, yes, b3 sin 3x, and so on. So a series of the form is like this is called a trigonometric series because trigonometric terms sine and cos are involved, and this is also called a Fourier series. Okay, the series trigonometric series can be a series of tan, cos, or anything, right? But this particular series involving sine and cos is called a Fourier series. Okay, so what we are going to do in this chapter, in this section, that is in Fourier series, is first I define periodic functions. So why I define periodic functions? See, periodic functions, if you define, say, as I can say, if I consider f of x, okay, f of x is equal to, say, x in the interval closed interval minus 2, 2. Okay, I have defined the function f of x is equal to x in the interval closed interval minus 2, 2. Okay, so what will be the graph of f of x? The graph of f of x will be like f of x is equal to x, right? So it's a V-shaped graph, you know. So in the interval minus 2, 2, it's going to be a graph like this, right? So this is your minus 2 and this is your 2. Yes. So in the interval minus 2, 2, f of x is equal to x. I have defined like this. Now if I extend it to the interval 2 to 6, like in the same way, that is this function, if I transformation I have given. Okay, so this is your 6, then this is your 4. Okay, so this function, the same function I have transformed to the interval 2 to 6, then I transform it to the interval 6 to 10 and so on. Okay, likewise in here also, so I can transform it to the interval minus 6 minus 2 and so on. So I am extending it to the whole real line. Yes, so actually my initial function was defined only in the interval minus 2, 2. Then I have I am extending it. Okay, so same thing I am defining. Okay, in the interval 2 to 6, then in the interval 6 to 10 and so on. Okay, so this function is periodic in the whole periodic. Okay, because the value at minus 2 is same as the value at 2, right? The value at minus 2, what is the functional value? Value at functional value, f of x is equal to x. Oh, I have drawn the graph of f of x equal to mod x. Well, let me change the definition. What I have drawn is the graph of f of x is equal to mod x. Okay, so I have extended the function f of x is equal to mod x to the whole real line. Okay, so f of x equal to mod x is a v-shaped function. So actually initially I defined it in open interval minus 2, 2. Now I have extended to the whole real line. Okay, so actually f of x is equal to mod x. F of x is equal to mod x defined for all x belongs to R is not periodic. Yeah, f of x is equal to mod x for all x belongs to R is not periodic. But by this function, you know, f of x is equal to mod x in the interval minus 2, 2, and extending it this way is periodic. Yes, it's periodic, and the length of the period is this 2 minus minus 2, that is 4. 4. Okay, so this is the length of the periodic function f of x equal to mod x. So its period length is 4 because I am extending after 4 units the same value repeats. So if I take the value at -1, that will be the same as -1 plus 4. Okay, so at the 3 also I will get the same value. Okay, the value at -1 will be the same as the value at 3. The value at 0 will be same as 0 plus 4. The value at 4, yes. The value at 2 will be same as 2 plus 4, that is 6, yes, and so on. So the value at uh, 10 will be same as 6 plus 4, yes. So what will be the value at 100? How will you write? Yes, how will you write? So write it in the form. So 100, see, 100 divided by 4, yeah, so this is 25. So 25 times, so this is so f of 0 plus 25 into 4 you can write, right? 100, yes. So the value at 0 will be same as the value at 100, yes. Yeah, so now value at 101, it's going to be f of 1 plus 100, right? So this thing is 25 into 4, so the value at 1 will be same as the value at 101 and so on, yes. So you can write it like this. Yeah, so this function, that is f of x is equal to mod x, defined in the interval -2 2 and extended in this way, is periodic. Yes, so we can define periodic function. Now what we are going to do in this function is, we know the properties of sine function and cosine function. Okay, so many properties we know. It's periodic, with periodic 2 pi and so on, and we can differentiate sine function. Yeah, we can differentiate cos function, we can integrate that. Yes, so if we express, see here, actually here you are studying simple functions, but what in if we have some complicated functions, and if it's periodic, then we can express the feature is, we can express every periodic function in terms of sine and cosine function. Okay, so to study its behavior is easy, because we know the behavior of sine and cosine function. So what we are doing here is, we express every periodic function in terms of sine and cosine function. Okay, that's what we are doing in this chapter. Okay, so we have, so in the very beginning, I have written a formula, right? This is the Fourier series, that is a series of the form, yeah, a naught plus a1 cos x. So this is the general thing. It's going to be general formula is going to be like this, that is a naught by 2 to some constant. Okay, to determine the coefficient, we have written in the form a naught by 2. Yeah, so it's a constant. Again, with the a n, cosine terms are involved. Okay, and with the b n, cosine sine terms are involved. Okay, so we have a naught, then summation n equal to 1 to infinity a n into cos n pi x by n, plus summation n equal to 1 to infinity b n into sine n pi x by n. Now we have, if a given function is if a function f of x is given, we can express, if the function is continuous at the point x, then we can write f of x is provided f of x is a periodic function. Okay, and L is half the length of that period. Okay, so we'll come to it later. Okay, so we have, if we have actually what we are doing is, we express periodic functions which are continuous in this form. Okay, and at point of discontinuity also we will get a series similar to this. Okay, but the value will not be equal to f of x, that we will come across. Okay, so here actually we are going to study about Fourier series. So I will just, yeah, Fourier series. So we will start with Fourier series. Yeah, so see, we can in this chapter we can express some particular functions, that is periodic functions, we can express as infinite terms of sines and cosines. So actually that trigonometric series is called Fourier series. Okay, now we will come into how to determine the coefficients and all. Yeah, so before we, so this is the series. Okay, naught by 2 plus summation. Yeah, they have used the notation m, and I have written m, doesn't matter. Yeah, so a naught by 2 plus summation m equal to 1 to infinity am into cos m pi x by l plus bm into sine m pi x by l. Okay, so a series of this form is called the Fourier series. Now this converges. Okay, if it converges to a function f, we can determine the coefficients a naught, am, and bm. Okay, Now, in my last lecture, I have defined periodic functions. Okay, so let me, and I have defined what's meant by fundamental period or primitive period and all. Now, let me tell you a few more features about periodic functions. Yes, so we know sine function and cosine function are periodic, right? Is sine plus cosine, that is sine theta plus cos theta periodic? Yes, is sine theta plus cos theta periodic? What's your answer? Yes, we will just see whether sine theta plus cos theta is periodic or not. Okay. So let's have a look. See, sine function, that is sine theta, we know sine 2 pi plus theta is equal to sine theta, right? What about cos theta? Cos 2 pi plus theta is equal to cos theta. So sine theta and cos theta are periodic with period 2 pi, that is primitive period 2 pi. Now what about sine theta plus cos theta? Yes. So sine theta plus cos theta, if I replace theta plus 2 pi, theta with 2 pi, then sine of theta plus 2 pi plus cos of theta plus 2 pi. Yes, that is same as 2 pi plus theta. So that's going to be sine theta plus cos theta, right? Sine theta plus cos theta. So, see. So, if my f of theta is sine theta plus cos theta, yes, then f of 2 pi plus theta is sine 2 pi plus theta plus cos 2 pi plus theta, that also equal to f of theta. So if sine and cosine, since sine and cosine are periodic, their sum is also periodic. And what about their difference? Their difference is also periodic. Yes, sine theta minus cos theta is also periodic with period 2 pi. Yes. Now what about product? If product is product of two periodic functions periodic? Yes, they are periodic. Yes. So these are some features. Okay. So if we have periodic function f of x, so say f of x and g of x. Suppose f of x and g of x are periodic with period L. Okay. F of x and g of x are periodic with period, say period. What is the notation we are using? Yeah. F of x and g of x are periodic with period T, I may use. Yeah. So f of x and g of x, that is f of x plus t is equal to f of x, and g of x plus t is equal to g of x. Okay. See, same period must be there. Okay, otherwise we have to find the LCM and all. Yeah. So if f of x and g of x are periodic with period t, then we have f of x plus t is equal to f of x, and g of x plus t is equal to g of x. Now what is so f plus g? So my question is f plus g periodic? Yes. So is f plus g periodic? Now f plus g of x plus t, what is it? So it is going to be f of x plus t plus g of x plus t, right? Now since f is periodic with period t, we have this is equal to f of x, and since g is periodic with period t, we have this is equal to g of x. So that I can write as f plus g of x, right? F plus g of x. Yeah. F plus g of x plus t is equal to f plus g of x for all x. So this shows that f plus g is periodic with period t. So if f and g are periodic with the same period t, then we have f plus g is also periodic. Yes. Now what about suppose we have a periodic function f with period t. Yeah. So we have f of x plus t is equal to f of x. Now what about a scalar multiple of this? So my question is, so f is periodic, that we know. Is a constant multiple of f periodic, that is c times f, is it periodic? So what is c times f of x plus t? We can take the constant outside, right? So this is c into f of x plus t. Yes. So that's equal to c into, since f is periodic, f of x plus t is f of x. Yeah, this is equal to cf of x, right? So cf of x plus t is equal to cf of x. So that shows that a constant multiple of a periodic function is periodic. Yes. Now let me define. Let me ask you one more thing. So you might have studied odd functions and even functions. Okay, that's also important here. Odd functions and even functions. Can you give an example of an odd function and an even function? Yes. So, yeah, come up with some examples of. So, this is your homework. Give me some examples of odd function, odd functions, even function, and neither even nor odd. Okay, neither even nor odd functions. Okay, give me some examples of odd functions, even functions, and neither even nor odd functions. Yes. So then we will explain it in my next lecture. Yeah. So I will start here. Yes. So we have, yeah, capital F of x is equal to, so a constant, if, see, if f and g are any two periodic functions with common period t, that's important, yes. So if f and g are two periodic functions with common period t, then their product fg and their linear combination c1f plus c2g are also periodic with period t, yeah. So they have shown the linear combination thing. Let capital F of x is equal to c1f of x plus c2g of x. Then capital F of x plus t, that is equal to c1 into f of x plus t plus c2 into g of x plus t. So that's equal to c1 into f of x plus c2 into g of x, that is equal to capital F of x. So what we have got, capital F of x plus t is equal to capital F of x. So this shows that capital F is periodic. And what was capital F? Capital F is c1 f of x plus c2 g of x. So that, this shows that if f and g are periodic with a common period capital T, then their linear combination is also periodic. Yes, hope it's clear. Yes. Now, yes. Now, orthogonality of the sine and cosine function. So, when do we say that two functions are orthogonal? Yes, if the inner product is 0, right? If the inner product, see, to describe a second essential property of the function sine m pi x by l and cos m pi x by l, we generalize the concept of orthogonality vectors. See, the standard inner product of two real valued functions. I don't know whether you have studied inner product and all. So, the standard inner product of two real valued functions u and v, the interval is defined like this. That is inner product. Inner product, for inner product, actually, we use the notation like this. Okay. See, inner product of two functions u and v are written like this: u comma v. Inner product, this is the notation. So in this textbook they have used curly bracket, open brackets, but this is the notation usually used. Okay. So yeah, the inner product of two real valued functions u and v on the interval of closed interval alpha beta is defined like inner product of u comma v is equal to integral alpha to beta u of x into v of x dx. Okay. Now the functions u and v are said to be orthogonal if their inner product is 0. That is if the integral thing is equal to 0. That is if integral alpha to beta u of x into v of x dx is equal to 0. Okay. Now, a set of functions is said to be mutually orthogonal if each distinct pair of functions in the set is orthogonal. Okay, a set of functions is said to be, that is if we have more than two functions. Say if you have u, v, and w. Okay, then that set is said to be mutually orthogonal. Yes, I will show you. If you have three functions, say if you have three functions, say u, v, w. Yes, this set is said to be mutually orthogonal if u and v, that is inner product of u comma v is equal to 0, then inner product of v comma w is equal to 0, and inner product of u comma w is equal to 0. That is all of them must be any distinct two. Yes, inner product u comma u we are not saying. Inner product of u comma v comma w, then u comma w. Yes, inner product of u comma v or inner product of v comma u. Okay, that was, if it's 0, it's the same thing. So if inner product of any two is 0, then we say that they are mutually orthogonal. Okay, if each distinct pair of functions in the set is orthogonal, then we say that the set is mutually orthogonal. Now here are some examples of mutually orthogonal set of functions. Okay, see, this we will come across in our Fourier series. So this type of integrals are all important. This type of integrals is the thing we come across while doing Fourier series. Okay, so integration, I told you, be thorough with integration, right? So we see integral minus L to L cos m pi x by L into cos n pi x by L dx, that is equal to 0 if m not equal to n, and it is L if m equal to n. So these are some values of integration. If you know this, it's okay. Otherwise, you integrate and find out. Okay, no problem. We can integrate and find out. Okay. Yes. So some now Euler formula. Yeah. So I told you, see, what we do is if we have a function f of x which is periodic with period 2L, then the Fourier series, okay, if the function is continuous, suppose the series converges, suppose the Fourier series converges, then it converges to f of x. Okay, then we can write our f of x as f of x is equal to a naught by 2 plus summation. I will use the notation n. Okay, that's more convenient. So summation n equal to 1 to infinity a n into cos n pi x by L plus b n into sin n pi x by L. Okay, where a naught, a n and b n are given by the formulas. Yes. So we have the formulas to determine the Fourier coefficients. Yes, is that given here? No. And I will write it down. Yes, it's given. Yeah. See, where A naught is given by the formula 1 by L integral minus L to L f of x into cos n pi x by L dx. Yeah, where n is equal to 0, 1, 2, 3, etc. So for A naught, you will get A naught is simply 1 by L integral minus L to L f of x dx. Because when n equal to 0, cos n pi x by L is 1, right? So in the Fourier series expansion, you will get A naught as 1 by L integral minus L to L f of x dx, and the an for n equal to 1, 2, 3, etc. that's equal to 1 by L integral minus L to L f of x into cos n pi x by L dx, and bn bn is equal to 1 by L into integral minus L to L f of x into sin n pi x by L dx. Yes, so bn is this thing. Yeah. Bn is equal to 1 by L integral minus L to L f of x into sin n pi x by L dx. Yes. So these are called the Fourier coefficients, and they are determined using the Euler formula. Okay. So let me come to it. So just write down Fourier series of 12 periodic functions. Actually, we use capital L to denote period. Okay, in this whole chapter, we'll be using capital L to denote period. So the period we denote here, we are taking the period as 12. Okay, Fourier series of 12 periodic function. Yes. So the Fourier series of 12 periodic functions, small f of x. Yeah, the Fourier series of capital 12 periodic function small f of x initially defined over the interval minus L less than x less than L is given by the Fourier series. So the Fourier series is f of x is equal to is given by the Fourier series f of x is equal to a naught by 2 plus summation n equal to 1 to infinity. I can write in a single summation n equal to 1 to infinity a n into cos n pi x by L plus bn into sin n pi x by L. Okay, n pi x by capital L. Okay, so the period is 12 and we are taking half the period. Okay, here. So f of x is the Fourier series expansion is given by f of x is equal to a naught by 2 plus summation n equal to 1 to infinity a n into cos n pi x by L plus bn into sin n pi x by L, where a naught is equal to, yes, where a naught is equal to, a naught is given by 1 by L integral. So the period is 12. You should not forget that. Okay, the period is 12 and we are taking half the length of half the period. Okay, so a naught is equal to 1 by L, so, integral minus L to L f of x dx. Yes, a naught is equal to 1 by L integral minus L to L f of x dx. A n is equal to 1 by L integral minus L to L f of x into cos n pi x by L dx. Yes, f of x into cos n pi x by L dx, where n equal to 1, 2, 3, etc. And bn is equal to 1 by L integral minus L to L f of x into sin n pi x by L dx. Again, n equal to 1, 2, 3, etc. Yes, 1, 2, 3, etc. Yes, so this is called Euler formulae. So the coefficients of the Fourier series are determined by the Euler formulae. A naught is equal to 1 by L integral minus L to L f of x dx. A n is equal to 1 by L integral minus L to L f of x into cos n pi x by L dx. Bn is equal to 1 by L integral minus L to L f of x into sin n pi x by L dx. See, in some textbooks, you will see the Fourier series expansion as a naught plus summation this thing. Okay. So, in that case, if it is simply a naught, you are here you will have a naught is equal to, instead of 1 by L, you will have a different you will have a constant here. Okay, so if it is simply a naught, then you will have the formula of a naught as 2 by L integral minus L to L, so on. Okay, so to avoid that, to have in the same formula, we have written a naught by 2. So we will follow this formula. Okay, f of x is equal to a naught by 2 plus summation n equal to 1 to infinity, this thing. Yes, hope it's clear. Now, so be thorough with the formula. Actually, this is the actually, if you know this single formula, you can do the problems in this chapter. Then we have particular cases like if 2L is 2 pi, or if 2L is something, then you have some particular cases. Okay, so if 2L is 2 pi, and if the interval is from minus L to L, that also matters. Okay, initially it's defined in the interval minus L to L. Now the formula varies according to whether it's defined from 0 to 12, yes, and so on. Okay, initially if it's defined in the interval 0 to 12, then we have a slight difference of formula. So we have particular cases like L equal to pi, yes, and so on. So for that we substitute and simplify and we'll get the formula. But this is the main formula you have to study. Then all other things you can substitute and simplify. Yes, so be thorough with the formula. So we will start doing problems in our next class. Okay, so we'll stop here for the time being. So in the next class, come up with examples of even and odd functions. Okay, so I will stop here. Thank you.